Okay, let's move on to further exercises. Basically, I just put all the hard problems about domain in this section of the notebook. They're all about domains. Let's begin with relatively easy problem. 7.1, find the domain in which the given function is 1 to 1, and then find its inverse function, and then the domain of the inverse function. It's all about domain. About finding out an inverse function, we talked about it before. Switch x and y and solve for y. It's not that bad. How to find out the domain? Well, if you have quadratic function like that, by the way, as you can see, the graph of this function looks like this, and this clearly is not a one-to-one function. It fails the horizontal line test. But if I simply take right-hand side half, apparently the axis of symmetry is x equals to 1, so take x is greater than or equal to 1 and take the right-hand side, then that is one-to-one function, and we can consider inverse function from there. How do we actually find out? Here's a technical detail. Set it up as complete square, like this, and then, well, x squared minus 2x after factoring, and then add 1, subtract 1 to get 0, and x squared minus 2x plus 1 is complete square, and what's left is over there, and then we have the vertex form. And the vertex form is here, so what do we have? Axis of symmetry is, that's when this one is equal to 0, so x is equal to 1. So if I get x is greater than or equal to 1, then I'm going to get the domain in which my given my function is 1 to 1. Also, look at this y, and this is always negative because negative times square number. And then this is as big as 0, that's big as you can get. So whole thing is less than or equal to negative 2. So that's the range. So that's going to be the domain of your inverse function. You can find out like this. Or you can actually algebraically manipulate this equation. So for, after switching x and y, so for y, get the inverse function. And that'll have square root expression. And from there you can find out the domain of the inverse function. Either way you can work out, but in any case it's all about domain. Other kind of problems, quadratic function problem, similar. You have to express those as vertex form. If you have square root function, then the domain of this function is relatively straightforward. The inside of the square root has to be greater than or equal to 0. Find out an inverse function, then inverse function will be a quadratic function. But then again, that's not going to be the function, the whole function you're looking for, because that inverse function has to be really an inverse function. So it has to have some restricted domain so that it is really an inverse. But how do you find out the domain? It is all about this complete square and vertex form. Now, next type of problems, when we have just a denominator, all we have to do is set the denominator equal to 0. This is really simple example. Excuse me. The denominator is just quadratic, so just factor it, and what do you get? X is not equal to negative 4, or x is not equal to 1. So in the set of real numbers, entire real line, just expunge out x equal to negative 4 and 1, and then take the left-hand side, less than negative 4, between negative 4 and 1, and then greater than 1, and we have these intervals. What if we have a little bit more complicated denominator like this quadratic trinomial? Well, it is also a trinomial that you'll have to use technique for quadratic. So I expect you to study all these and really master the factorization. If you screw up in factorization, you can never succeed in this course, because you see, this factorization thing shows up all the time, and usually it shows up in step 1. So if you just miss it, and everything else is just all gone. And here it is too. You have to factor this quadratic trinomial quadratic trinomial into quadratic method, I just change the sign by multiplying everything by -1. Okay, that's an extra step. And then here's factorization. It's basically step 1. If you screw up here, you're doomed. Now, 4x squared plus 3, that's irreducible because square plus another positive number is always positive, never 0, so I cannot factor it any further. But x squared minus 1, that does reach 0, so we have linear terms. So x plus 1, x minus 1, those will give me zeros of denominator, where we'll have to expunge those. And then what's left will be these interval, negative infinity to negative 1, between negative 1 and 1, and then 1 to positive infinity. Okay, those were relatively easy. All you have to do is set up the denominator equal to 0, and those are okay. I'm not overdoing anything. Okay, maybe 7.1 example were. Okay, let's talk about 7.3 examples. Now I have to be really careful not to overdo this. The first problem is appropriate. We have just one radical, so inside of this radical has to be greater than or equal to 0, and that inside is pretty simple. All I have is 1 minus 3y. That has to be greater than or equal to 0. That's easy. It's just linear inequality. Just use typical technique. You're gonna get y is greater than or equal to negative 1/3, excuse me. So in an interval notation, we have negative 1/3 to infinity, inclusive of 1/3. So y equals to 1/3 is okay. In that case, we have square root of 0. That's okay. Now we have more troublesome problem. We have square root, and also we have denominator. Somehow we have to combine those two. Okay, let's do it. Inside of the square root has to be greater than or equal to 0. So we have 4 minus x squared is greater than or equal to 0. I can't really think straight if my leading coefficient is negative. So I just multiplied everything by -1, so that x squared minus 4 is now less than or equal to 0. Factoring further, we have x plus 2 times x minus 2 is less than or equal to 0. So we have these two zeros with multiplicity 1. What do we have? We have this kind of diagram. X equals to 2, x equals to -2. Those are the zeros. And then the right hand side, this expression is positive, greater than 0. In the middle, less than 0. And then cross the out multiplicity, now greater than 0 again. They're all odds, so we have sign changes all over. The middle region is what I want because x squared minus 4, or this factored form, is negative. And x equal to -2 is okay, so -2 to 2, good. But is that all? No, not really, not yet. Denominator is troublesome. We have to consider that one too. Because this is domain, so everything has to make sense. Not only this radical, but also this denominator has to be valid. So set the denominator not equal to 0. That's going to give me a quadratic equation, kind of like this. And then we have to expunge out x equals to 1 and x equals to -2. Because those are the solutions. That's when the denominator becomes 0. So in the previous interval, expunge x equal to -2, so now it's hollow dot. And expunge out x equals to 1, so we have two pieces of intervals now. And then we have -2 to 1, the left hand side, and then 1 to 2. And x equals to 2 is okay, that's when the numerator is 0. But x equals to 1 is not okay. Let me see. Let me draw a graph of this. And then we have this kind of graph. Okay, that's great. When x equals to -2, we have vertical asymptote, which means x equals to -2 is not allowed. When x equals to 1, we have vertical asymptote. X equals to 1 is not allowed. Not surprising, because we have 0 in denominator there. But at the right hand side, at x equals to 2, we have abrupt ending without any kind of asymptotic behavior. That means at that end point, y-coordinate value is well defined. That's when the square root is 0. Square root of 0 is okay, square root of 0 is 0. So x equals to 2 is part of the domain. Now, what if we have more than one radical and then denominator? Well, we'll have to, okay, let's consider that. In that case, we have to consider first radical and then the second radical and set both of them greater than or equal to 0. So we have an interval or number of intervals there, an interval or some number of intervals there, and we have to find out intervals in which everything is valid. So everything has to be shaded in there so that not only one radical but both of them are valid. And then finally we have to expunge out the denominator. Kind of goes like this. First radical, we have the numerator in the numerator. This one has to be greater than or equal to 0. We have this inequality. And solving that inequality, you get x is less than -3, less than or equal to -3, or x is greater than or equal to 1, or in interval notation, -∞ to -3, or greater than or equal to 1 to positive infinity. They are both odd multiplicities, so we have sign changes. So plus from the right hand side, and across odd multiplicity we have minus in the middle, and then plus again. We have to take plus part. How about the other radical? X plus 2 has to be greater than or equal to 0. That one is a little bit easier because this is just linear, and this is the diagram. And when x is greater than or equal to -2, this thing is valid. So in which interval both of them, both radical, are valid? We have to find out interval or intervals in which we have shading. We have those thick blue shading for both of them. And here we go. When x is greater than or equal to 1, or in interval 1 to positive infinity, both radicals are valid. -2, -3, those points were there, but those are not. Everything else, or left hand side, those are all out. Now we have to consider the denominator. Set this denominator equal to 0 and solve this radical equation, and then get x equal to -1 or 2. And one of them is extraneous, and then one is valid. So x equals to 2 is a valid solution. We have to consider that and expunge that one out. So in a previous picture we had something like that, greater than or equal to 1, so 1 to infinity, but x equals to 2 is no good, so throw that away. And consequently we have these two, 1 to 2, and then 2 to infinity. There goes the domain. Let's see. Let me show you the plot. I hope this battery of this laptop holds up. Okay. Okay, let's go a bit further. So we have abrupt ending at x equals to 1, which means x equals 1 is okay, the y-coordinate is valid. At x equals to 2, we have vertical asymptote, so we have to expunge that out. And then we have two curved pieces, 1 to 2, and 2 to positive infinity. And we have this domain here. Bracket part is related to abrupt ending. Parentheses, either positive infinity or vertical asymptotes.